Hi everyone, I hope you are doing well. In today's video, we are gonna explore a hydrogen energy system which is connected with photovoltaic or PV panels in order to meet a household's electricity demand. We will be working on this project using TRNSYS software, as we did. But before we dive into the design, let me first give you a quick overview and also a brief explanation of the concept behind it. As you know, one of the main challenges with solar energy is its intermittency. Since we can generate power at night or during cloudy climate, that's why off-grid or standalone solar systems need a reliable backup energy source. This backup can come in different forms, such as batteries, diesel generators, or even hydrogen systems. In this video, we will be focusing on the hydrogen option, specifically a hydrogen energy storage system or HESS. So today's video is all about integrating power of hydrogen energy storage with solar energy and how this combination can provide more reliable and sustainable energy solution. The proposed system that you can see the schematic of it in this slide is designed to meet the electricity demand of a household using photovoltaic or PV panels. A specified number of PV panels are installed on the house roof or at another suitable location. It doesn't matter wherever it is, to generate electricity sufficient to cover the household's demand. As you know, the electricity demand for a common house can be about 5 kilowatts. On a sunny day, when solar radiation is high, the PV panels may generate more electricity than the household requires. So, this excess electricity is directed to an electrolyzer, where water is split into hydrogen and oxygen. The hydrogen produced in the electrolyzer is then directed to a compressor, which compresses the gas from ambient pressure to the pressure approximately about 200 bar. The compressed hydrogen is subsequently stored in a hydrogen storage tank. Since hydrogen has a high volume in its natural state, compression is necessary to reduce the volume and enable practical storage. This stored high-pressure hydrogen can later be utilized as an energy carrier for various applications. Moreover, in the case of generating less electricity compared to our demand for our household, we are going to use fuel cell. As you know, fuel cell is a device that is functionally opposite to electrolyzer, where hydrogen is combined with air and generate electricity for us. During nighttime or whenever the electricity is insufficient, the fuel cell will apply its role. This is the whole system we're gonna apply in TRNSYS software. We need to use different components, different control systems, and I will tell you in more details in the TRNSYS software environments. Well, let's move on to the TRNSYS software. As you can see in the TRNSYS software environment, one of the key components and key factors that must be taken into consideration is load modeling. Load modeling is an essential step for precise simulation. While we can, import different profiles of load from different sources, like tram build that we have it in TRNSYS software. Here in this study, we want to define the load internally using two main parameters. The first one is monthly ratio. Monthly ratio is a coefficient between 0 and 1 applied over 8,760 hours. I mean the total number of hours in 1 year. It allows us to scale the annual load according to monthly variation. The other one is dynamic load profile. This represents the time-varying nature of the load. In this case, the load fluctuates over time between minimum and maximum of 3.19 kilowatts and 6.39 kilowatts uh, respectively. A 24-hour period capturing the daily pattern of demand. Now, if we multiply the dynamic load across the hours of the year, we obtain an estimate of the actual billing load that we desire. Well, in order to plot the load over time, we set the y-axis, the left axis, with a maximum value of 10,000 watts. And also in the setting, the simulation stop time is set to 8,760 hours, equivalent to 1 year, And the time step for the simulation is set to 1 hour. Okay. Now, if we run the simulation, if everything goes fine, the simulation is executed under this setting. The resulting output provides the dynamic load over the year. That includes the national fluctuations, ups and downs in demand. Great. Now let's talk about components. As we discussed before, in order to run our simulation, we need to use several particular components that we named it before. So if we go to the hydrogen system library, we need a compressor for our simulation. In the electrolyzer section, let's choose the advanced alkaline, and in fuel cell, AFC alkaline fuel cell will be used. That's the alkaline fuel cell. Yeah, that's it. And in order to be a more readable and also more convenient layout, you can activate macro model and deactivate it whenever you want. Whenever you want to edit your problem, you can deactivate it. This will help you in order to reduce size and have more readable layout. Let's call it our macro model as load. Okay. As we discussed before, we need to use a control system for our simulation. Since we have an electrolyzer and also a fuel cell at the same time in our project, we are going to use a master control. A controller which is a suitable control system here and we go to let's go to the electrical section. We are gonna choose power conditioning. Now here we use power input is known that we are gonna explain it in further details. We are gonna talk about these components in more details and within more explanation since we have two of them in our simulation. So don't worry about that. We have almost selected the whole components we desired, if I'm not mistaken. But we need to model our hydrogen tank for our hydrogen gas, either real or ideal gas. So you can study each component here with more details and get more data here within its description. The real gas component will utilize van der Waals equation, while the ideal gas will use the ideal gas equation, I mean PV equals nRT, which may bring some errors, as you know. So if we don't want to have those errors in our simulation, we have to use the real gas component. So I'll remove this one, and this is our hydrogen system. But we need to add weather data and also solar panels, then connect them with together to complete our simulation. Yeah. So first of all, let me select weather data here. We're gonna choose a standard format and we will use TMY2. In external files, the default city is Madison. However, if you want to choose another city, you can browse and change the location as you desire. For this project, San Diego City is our location, and that's for our weather data. It's necessary to connect PV panels to the weather data. To do this, from Electrical tab, you can choose photovoltaic panels. You can choose Advanced Model or Basic Model. In this project, we're going to choose Basic Model with MPPT, which is an abstract of maximum power point temperature, which can work with best power points. Then you can import the PV panels characteristic from catalog. If we go to the tab, here we choose 9.23 amps for short circuit current, and we're gonna set open circuit voltage to 38.3 volts, and we leave the reference temperature as default, I mean 25 Celsius degree, and also we use 31.46 volts for our voltage, and also uh, let's see, 8.85 for the current at MPPT. Yeah, and it is needed to set temperature coefficient for short circuit current and also open circuit voltage. We're gonna choose 0.044 for temperature coefficient of short circuit current, and also minus 0.03409 for temperature coefficient. And also we set the number of cells wired in series is about 60, and module area we set it with 1 square meter. Another key point to consider here is our system sizing. By doing try and error approach, we set number of modules in parallel to 70. Now the PV panels are designed and ready to use. By connecting weather data to PV panels, we can match the properties here. We're gonna match dry bulb temperature to ambient temperature beam radiation to beam radiation for surface, sky diffuse radiation to sky diffuse radiation for surface, and ground reflected diffuse radiation to the same one. Let's see array slope to slope of surface, and also incidence angle of beam radiation to angle of incidence of surface. Yeah, that's it for PV panels. Now we can plot the PV panels output to ensure that our results are accurate enough. To do this, from Output tab, we choose Online Plotter. By connecting PV panels to our plotter, we can see the result. We match array power at maximum power point, I mean MPPT, to left axis variable that you can check it in your PV panel's output, which is in watts. Based on my prediction, I'm gonna set maximum magnitude to 2000 watts to get a good plot. Yeah, it takes a while to complete the plot, but that's okay. So this was for our solar system design, which was designed completely in addition to the load that was simulated and designed before. Well done. Now let's design our hydrogen energy system that you can see its components here. The most important part here is master controller. If we take a look at controller, you can see that number of diesel was defined in case of using diesel backup for our system in order to import its data here. And also it has a table for idling and rated power for electrolyzer and fuel cell. There is an input power, which is in our case is our load, and also hydrogen storage state of charge, I mean SOC. As you know, we haven't designed master controller yet, but the first step is master control design. So if we connect load to master controller, we'll see all possible micro outputs which is derived from micro components and now we can match the items here. Okay, so we match load to load, which they have similar units of watts. And for PV panels, we know that the output power of our panel is the input power of master controller. It will check whether the power is excessive or not. In case of extra power, it will deliver energy into the electrolyzer. But the key and significant item to consider is that since electrolyzer doesn't communicate with controller directly, we should use power to current component. To do this, by matching electrolyzer power to input power, so we attached output current of power to current into electrolyzer. So that's it for this part, but still we need to do one more connection in order to complete.